So here's a projectile problem. Somebody throws a rock with a velocity of 30 meters a second with an angle of 60 degrees above the horizontal. They're standing on a 50-meter cliff, and we can ask a lot of questions about this to try and get, try and use those projectile equations. So for example, how far away does the rock land? What time does it land? When does it reach its highest point? What is its highest point? Those are all possible questions. We always tackle projectile problems the same way. Vertical components and horizontal components of motion are independent of each other. The vertical component of motion is going to experience acceleration due to gravity, and so in that component, the object is going to accelerate towards the ground. Horizontally, we're going to ignore friction. There is no acceleration in the horizontal direction. And so this is going to affect the givens and the implieds, and it's going to affect the way we choose to solve this question. First thing we're going to do, though, is we're going to resolve this into its components. And so if this is 30 meters a second at an angle of 60 degrees, that means it's 15 meters per second horizontally, and that's going to be constant. So that's just a SOHCAHTOA problem. To find the vertical velocity, all I have to do is 30 meters a second times the sine of 60 degrees. And so this is actually closer to 26 meters a second right after it's been tossed. And so let's ask the how far away question first of all. What we're going to do is we're going to divide this up into vertical and horizontal components and treat each of those variables separately. Okay, positive x to the right, positive y is up, and so we have change in displacement, we have initial velocity, we have final velocity, we have acceleration, and we have time. Okay, displacement in the x direction, this is an unknown. This is in fact the thing that we want to know. Displacement in the y direction, we actually know that this is going to fly until it hits the ground, and it's going to be happening 50 meters below the release. Initial velocity in the x direction, 15 meters a second. We know that. That was a given. Initial velocity in the y direction, positive 26 meters a second. We know that. Final velocity in the x direction, 15 meters a second all the time. Final velocity in the y direction, we don't know. Maybe we don't care. Acceleration in the x direction, 0. Acceleration in the y direction, negative 9.8 meters per second squared. And time in the x and the y direction, in this case, as soon as it lands, it stops moving horizontally and it stops moving vertically, and so time is the same for both of these equations. Now, you'll notice that this is a rather paltry offering here in the x direction. All I know is how fast it's going. I don't know when it stops. I don't know how far it goes. The acceleration is 0. Basically, there's not too much I can find out from the x direction given this amount of information. Maybe if I knew how long it was going, maybe if that was part of the given information, I could calculate the horizontal distance, but it's not. I think I'm stuck. I don't think I can do anything in the x direction. As far as how far away, let's see. Final velocity in the y direction, I don't care. but I am given distance, velocity, acceleration. If I worked out time, that would tell me something in the x direction, and so calculating time is something that will help figure out how far away it lands in the x direction. And so I'm going to look for an equation. Just going to say that VF isn't involved. I'm going to say I want to know what time is, and I'm going to look for an equation that's going to do it for me. And I can see it's actually equation 3, my all-star equation, is going to do this job for me. So the change in displacement is equal to the initial velocity in the y direction times delta t, which I don't know, plus 1/2 times the acceleration in the y direction, which is negative 9.8, times delta t squared, which once again I don't know. This is going to land 50 meters below where it started. Its initial velocity is 26 meters per second. The time, I don't know. 1/2 times negative 9.8 is negative 4.9 meters per second squared, and this is times delta t squared. This becomes a quadratic equation, and so we're going to have to figure out what our a, b, and c are, and we're going to have to make it equal to 0. Who knew the quadratic equation would pay off? 26 meters per second times delta t minus 4.9 meters per second squared times delta t squared. Okay, there's my quadratic equation. So time is equal to negative b, so negative 26 plus or minus the square root of 26 squared minus 4 times a, which is negative 4.9, times c, which is 50, all over 2 times a, which is negative 4.9. So there's my quadratic formula all set up using this as a quadratic relationship. Okay. Time is equal to either negative 1.5 seconds, which would be sometime prior to release and probably down at the bottom here at the 50 meter mark. A second possible solution to this is this is the big winner. So I know that my time is 6.8 seconds. Now I've got everything I need really to calculate delta D in the horizontal direction, because the time is the same for both of these. So I'm going to use delta D equals, and I'm not going to do the 1/2 AT squared. I'm just going to do the V1 times delta T. And so delta D is equal to 15 meters per second times 6.8 seconds. All right, and that is equal to 102. And so depending on the question, sometimes it can be a little bit different. Exactly which variable we are after can sometimes be a little bit different, or the given and implied information can be a little bit different. For example, we just answered when it lands, then we were able to answer how far away. If we were asked for the highest point of flight, in other words, where does it reach its, or when does it reach its peak, or how high does it go, they're actually telling us that VFY is equal to 0. And so that would be filling in this piece of information here, not telling us maybe this piece of information. We'd have to calculate it, and we wouldn't know this piece of information. Okay, so just fill in the table. Make sure you're breaking it up into the two components. Just remember the vertical component is different than the horizontal component. Pull out all of the given and implieds for each one and select which one of those equations you think is going to work.